All right. I guess we can wait another 1 minute since there are always people coming late. How's everybody doing so far for this semester? Has everyone found a teammate? Cool.
For the proposal let's do, is there any guidelines?
Oh, yeah, I think if needed, I can come up with a guideline, but it's really simple, like just one to two page, with basically with some abstract and some background introduction and motivation, and possible like proposed like timeline, and how you're gonna distribute the work, and how you're gonna evaluate the outcome of your project, for example. Yeah. But yeah, I can try come up with something and share it on Canvas. Not really, yeah. But I will come up with like a templated outline. So in case you're curious about how to write a proposal. All right, so let's get started for today. So last time we talked about some optimization algorithms for optimizing a given function. For this lecture, we're going to do a little bit more advanced version of that, where we try to optimize something that's more hidden and black box, and we're given we're given more constraint in how we can query and evaluate the function we actually want to optimize, which is a more realistic setup. So some of the machine learning techniques that are involved, including, for example, Bayesian optimizations and reinforcement learning, or reinforcement learning with feedbacks at the end. All right, so some quick announcement. So we'll make a small syllable change to the geometric deep learning module. Basically, move one thing later in the semester on like inverse folding up to immediately be after the graph neural networks. And then the geometric deep learning 2 lectures will be sliding backward for 1 lecture. And the reason for that is we want to have some invited speaker on geometric deep learning. Basically, I think these are really good researchers in the field of geometric deep learning, and they're from actually UK, and they are the first author of the paper for actually our reading assignment 3, which is called Hitchhiker Guidance to Geometric GNN. I believe it's a very comprehensive and very well written tutorial paper, written by a few groups that are basically the founder of geometric deep learning. So I will share the paper very soon, next week, before our module began. And I wouldn't require a review for this reading assignment, so I would, because this is kind of very helpful for learning of this module, so I would encourage everyone to try read the paper and try to understand the material and use it as kind of like a textbook for this module. This might help you kind of interact with me and the speaker during the courses. So there might be like some, during the course question, which if you can call it maybe attendance. So we'll use that as kind of an alternative to writing a review in open review for this 3rd reading assignment. All right, so the guest speaker will be 2 weeks later, it's a Wednesday on the end of October. And then the next 4 lectures, the next lecture is still going to be graph neural networks, and after that we're going to continue learning graph neural networks and also doing inverse folding earlier in the semester. And then we'll move back to the normal like geometric deep learning topics, which the first one will be taught by me on the kind of the basics and the foundations of geometric deep learning, and then the second one will be given by this distinguished guest speakers. All right, so any questions so far? Cool. And then the schedule for homework and reading assignment will remain the same as the syllabus. It's just the course material, the ordering of the course material that's slightly changed here. Feel free to email us if you have any questions or concerns. All right, so let's go back to protein engineering and drug discovery. So as we mentioned many times in this course, we can think about this fundamental process of engineering or discovering a new molecule or a drug, being this iterative design, build, test, learn cycle, where through the cycle, we want to iteratively come up with some proposal, which is the design, and we build this, we build what we proposed, and we test them with some either in silico verifications or in vitro verifications, like high throughput assay, or doing animal, like clinical trials, and we gather some feedbacks from all of these verifications, and now we're in this critical stage where machine learning helps a lot in this iterative cycle, from first learning from the data, which is what we learned previously about kind of predicting the function or predicting the outcome. And from there, we want to ask a question like, can we use what we learned from the outcome to guide the next round of exploration or next round of verification to come up with perhaps better candidates that can get us to the true global optimum as soon as possible. So in the last lecture, we talked about like this optimization approach. Basically, if you have a function fx, optimization can be thought of as the problem of finding the optimum, either maximum or minimum of this function, where a lot of time because you know what the underlying function is, you kind of observe the function. So we call this kind of a white box optimization, because you can access the function and you can use, for example, the gradients of the function to do like Gibbs with gradient, is what we talked about last time, right? So, and you can do this for multiple rounds as well. However, for example, in this Gibbs with gradient, we kind of assume that this function f of x is already known, and it's the true oracle function that we try to optimize. Such that if you just follow the gradients or using whatever optimization algorithm on f, you will get close to the optimum of the function f of x with some number of within certain number of iterations. Like if your f is like well behaved, maybe with we can assume maybe some continuity or some Lipschitz constant bounding the kind of how yield shape the function is. A lot of time the optimization problem isn't that hard. However, in real life use cases, the optimization is much harder. The issue here is that fx is not exposed. And we're only getting partial observation of f of x, which is usually also very noisy. So in real life, we're operating on an approximation of, or a surrogate of the true underlying function that we're trying to optimize, which is oftentimes also a very complex function. And secondly, because we can't access the true functions, we're only allowed to use a limited budget on which part of this function we can observe. So oftentimes we call this kind of problem black box optimization problem with kind of limited budget to observe the space. So the key of solving this kind of problem is very important in a lot of these iterative optimization problem in protein design, or in general a lot of like even material design or other area that requires kind of querying and optimizing a hidden and very expensive to evaluate function. In our case, it could be like human evaluation or lab evaluation, or even running this Rosetta energy function, or molecular dynamics is not very cheap. It is still, even if you run everything in silico, it still could take like a very long time to get what we want. The more accurate we want, the longer it can take. And in terms of design, we're also using a lot of the generative models that help us to kind of do some data-driven approach to kind of come up with a good prior on what space we want to search. So we basically try to use machine learning to, in this setting, where we both try to use machine learning to learn a robust estimator under this limited data regime, usually require learning about the uncertainty as well as just the predictions. At the same time, try to come up with efficient iterative optimization algorithms that try to balance the exploration and exploitation trade-off. Basically, we don't just want to greedily optimize the function we have at hand because it's just a proxy. We also want to factor in the potential upside of just observing something new, even if it's not optimized. And additionally, we also have a lot of these pre-trained kind of experts' knowledge, either from a data-driven pre-trained language models, or you could also have like physics-based models. A lot of these priors, during this optimization procedure, we might also want to consider like try to make use of these good experts and try to leverage the existing knowledge in this pre-trained model. So I think essentially this is kind of the overall problem setting, and a lot of different approaches are introduced for this under this framework. So in my point of view, I think there are mainly three realms of methodologies under this iterative optimization with kind of limited observation scenario. A lot of them actually involves some probabilistic modeling of the world. The first approach that we're going to talk about today is Bayesian optimization, which is exactly set up to kind of solve this problem of solving a black box optimization with smallest number of acquisitions as possible. However, there are also alternative view to this problem. For example, we can consider the problem of optimization as a generative problem, which we actually talked a little bit about it last time when we introduced skips with gradient, right? Essentially, instead of doing gradient optimization, you also try to like sample from an underlying distribution that is kind of proportional to the function or reward that you care about. So oftentimes you get slightly like better exploration if you do like if you factor in this kind of stochasticity in this optimization process. And on the other hand, we also have a lot of tools in doing this kind of sampling. And you can consider like if you have some generative model as a prior, right? Or you just have a good some domain knowledge that can give you already limit your space to a reasonably good space. Then you're given like a prior model where you could sample from. And with this limited observations, you effectively can update your belief with the observation you made, and you can do this posterior update to the prior function. And if we sample with this posterior, we'll be able to get close to what the real world objective leads to, by also limiting ourselves to effectively the region that is most we believe most likely to be positive. And then the third approach is reinforcement learning, which we basically try to make everything further more black box and just try to come up with certain policy, or basically policy can mean like some way of come up with like generating or propose some new candidates to test. And we try to weight our policy by this reward, which reward is what we try to optimize. So I think different approach will have different use cases and their own like strengths and weaknesses. But I've seen like all of these approaches being quite used a lot in the current like molecule design use cases. So first of all, we're going to talk about the Bayesian optimization, which if like use a single sentence to summarize this objective is to maximizing a costly to evaluate black box function with fewer queried samples. So to formally describe the problem, we want to find the true minimizer or maximizer of a function f of x, where f of x is hidden. And usually for BO, they kind of assume a bounded domain, because you want to, when you run this search, this optimization like a search, you're usually like effectively running a search, and it makes it easier if you kind of assume that you're not searching in unlimitedly like wide domains. But this is just a kind of a common assumption that usually is satisfied. So where the f here is first, we don't know any information about f. We don't know its gradients. We also don't know any like higher order moments of the function. And it is usually expensive to evaluate, but it is accessible. And there is some assumptions made about this function, like Lipschitz continuous. And the problem of Bayesian optimization is to try to come up with a strategy where the strategy is defined using these 3 steps. The first step is you iteratively query a small set of the point, and you reveal the true label of this point by evaluating your function at this point. And then you run a surrogate, and then you fit a surrogate model, which we believe the model can be much cheaper than what the actual true function is, and they can be estimated just from these smaller sets. And once we build this model, we would kind of use this model to roll out the next round of points that we want to query. So there are kind of three aspects of this model. I think three aspects that is specifically required in Bayesian optimization. The first is to the existence of the surrogate model, which means we need to come up with a model family to learn this cheap surrogate function. And secondly, we hope that this model is Bayesian or probabilistic. It needs to reflect both the predicted, predicted value of given the current knowledge, but it also have to reflect the uncertainty due to the lack of observation of the rest of the domain. And lastly, we want to when we try to roll out the next round of samples, we also need to consider all of the possible outcomes from this model. So it's kind of like a posterior marginalization again, where you need to consider all possible predictions for a value for a sample before you decide whether or not you want to query it or not. So essentially what's important here is the notion of uncertainty, which we believe in Bayesian optimization is the key to balance exploration and exploitation. For example, assuming we have acquired 3 points so far, and this is a minimization problem here, and this is our current best point that we observed, right? So if we're fitting some deep neural networks or some function on these 3 points, there are actually essentially infinite possible solutions that can fit this data well, right? Depending on what family we're using and like what loss we're using, we kind of outside of these 3 points, the model could have a lot of different way of generalization. This is what we also taught about in the class of uncertainty aware models. So in this case, like, well, you would ask, where should we evaluate next, right? I guess this is also a question to the class. Like, if you are in this situation, what do you think could be some strategy that you might take to hedge your bets for the next point? Interpolate between 2 points. So you kind of you're defining some like safe way of doing interpolation between the points. So, but you still kind of want to concentrate on one way of doing interpolation. Yeah, interesting. So that's kind of sounds kind of like relying on some kind of mean estimation. Yeah.
Just search the neighborhood of the current best.
Yeah, I see. So assume kind of a local, like continuity and.
Well, I mean, assuming which is funded,
I see. So, but in this case, like, what if there's a third point that's far away from the current set, but like this upside that this point might actually turns out to be very good, but because it's too far away, it's like essentially unable to extrapolate what you've observed on this best point to that point. So that's kind of like the struggle that we're having here, right? Any other opinions here? Actually, in the slightly orthogonal domain called active learning, where the goal is try to learn the function as quickly as possible and collect points that enable us to learn this function as quickly as possible, they have a strategy just try to spread out their bets, like try to kind of evenly cover the space or like cover the space they're most uncertain about. And they believe that collecting information about those points will give us a lot of information about this function. But we are in a slightly different regime where we actually we want to be slightly greedy because we're doing an optimization problem, and sometimes we actually don't. We may have the assumption that maybe for some area that is too low value, there isn't too much value exploring there as well. So the slightly different mindset here is we have this optimization thing in mind that slightly changed the landscape where instead of going from pure exploration, we start to also do exploitation. So actually one naive strategy is called expected improvement, where this is one way of doing acceleration functions. You could basically draw like a horizontal line where of your current best values and just say anything that have expected value above this point, since we're solving the minimization problem, there is no value go into explore them further. I only want to focus on area that has potential to improve the function. So the mindset here is like you only care about making improvement, but at the same time you want to consider all possible values that you can predict at this position. Therefore, you take the expectation of the prediction. So for these two things that we're using here, we call this this model here surrogate model, which is a lot of type of Bayesian model, and we call this function that we use to decide where we query the next point acquisition function. And so this problem becomes iteratively get some points, fit a surrogate model, and calculate the acquisition function, and then optimize on the optimize deterministically on this acquisition function space.
So just to make sure I understand, so you can have a high expected improvement if you have high uncertainty about evaluation,
Yeah.
or it's just close by to your point that
Yes.
already has a good value.
Yeah, exactly. Or like somehow your model, I mean, that's likely impossible, but maybe your model extrapolate like in the upward direction, such that the model believes that you have improvement in that direction. Okay, cool. So if we look at the setting again, this is illustration of the entire kind of black box optimization framework. We go from at each round we repeat it for n rounds, and each round we do some observations, and these observations can be a single point, which is easier to analyze for, and usually the most optimal case is you make a single observation each time and you update your model frequently. But there's also a batched BO setting where because it's too expensive to query one point and wait and then do another experiment, it's usually much easier if you do things in batch. So there's both a batched BO setting where you have to query k points instead of just one point at each point, and you also want to hedge out your bets over this k point, basically diversify your k points such that you don't spend repeated effort in similar points. And then so again, the two key point here is to decide what surrogate model we use and what acquisition function we use. So in terms of surrogate model, actually there are a lot of different families that can give you uncertainty estimation. We actually talk about a lot in the deep uncertainty model class, where effectively, for example, using a deep ensemble model or a Bayesian neural network model for this problem. However, there's one model that is very simple and very easy to compute. However, it turns out to be very effective in the kind of BO community. Is called this Gaussian process model. To be clear here, why GP might be very effective is so this BO problem is usually operating in a low number regime. So even if we know kind of deep ensemble can predict uncertainty in some degree, but it's still a neural network, and the training and optimization of neural network is still non-trivial. So there are cases where you just have to do a extremely low number optimization regime, and in that case, deep model do not usually necessarily outperform simpler models. So Gaussian processes is kind of a very expressive and very strong model, but at the same time, it is kind of mathematically grounded for measuring certain kind of type of Gaussian uncertainty, even with a small number of data points. It is kind of a belief that it gives you kind of a very nice way of modeling uncertainty, even in a low number regime. And it of course have its own problem. At the end of this part, you might figure that problem by yourself. But to start with, the Gaussian processes is different from a single Gaussian function, because Gaussian it's not a model by itself. It's actually kind of a distribution over model. So it's actually processes where what we try to define here is basically a probability of the values of a set of variables, assuming that we have a set of variable x and their corresponding function is modeled by this f of x, where we believe that if these points are correlated in this point consists of a Gaussian process, we come up with this assumption that the function value of this point are modeled by this multivariate joint Gaussian distribution, where this joint Gaussian distribution will have the mean function of m of x or mu, and its variance is characterized by this covariance function. Basically, for every pair of the points, we believe that for this sets of points, their value distribution fall under this multivariable Gaussian distribution. So this is like both the mean and the variance here can be multidimensional. It's just kind of turning things into from a scalar to like a vector. So without losing of generality, this model can generalize to higher dimensional space. So you can also, like, if you're doing like high dimensional regression problem, you could do like maybe doing multiple objective at the same time. You can also extend this framework to modeling, multi-objective optimization. But for simplicity, we're kind of talking about single objective here. So we just assume f of x is like y equal to f of x is like a scalar reward or scalar value. F of x is a distribution of a single value, of a single variable y, where y is a function that's related to x, and its distribution is characterized by this multivariate Gaussian. So for the multivariate Gaussian, we know that its joint probability can be characterized by this function here, which is essentially a function of the mu, which is the mean, and this covariance function. And the covariance kind of tell you like which direction that the value of the two variables varies similarly or dissimilarly. There's a very nice property about Gaussian. First of all, like the linear functions of Gaussian variables are also Gaussian. We also know their explicit forms, and more importantly, the conditional probability of a Gaussian distribution is also a Gaussian, and which we also know how to write a form for. So this gives a very nice property in like when we consider like marginalization, where basically if I want to compute the likelihood of a given training set, we can marginalize everything else out and only focus on the sets of variables. And at the same time, we can do posterior update, where basically condition on certain variable and its value being observed, what is the distribution of a new variable y given x. So this property gives like this closed form solution for basically all the like training and the posterior inference of this GP model, which makes it very simple to use. Questions? No, because the covariance matrix assumes independency. The covariance matrix effectively captures the correlation between the variables. So you could maybe, if you have a very strong prior, you could maybe enforce some like isotropic Gaussian on the diagonal. But I think usually it is ideal if there is some correlation in the data, such that you could extrapolate, using the data. And yeah, I think the good question you ask is like this covariance function, like how we parameterize the covariance function. So it's actually part of the basically what we call like prior design. Basically, the model, like this covariance function, it doesn't need to rely on the value of the x. It just tells you like how likely they, the variance, like how much they vary together, right? So even without observing of y, you could come up with kind of a prior model just using a mean of 0 and a defined covariance function over the x directly. That will already give you a prior distribution over functional space. And this covariant function just tells you like how closely related the value of different x is. So this is kind of very similar to like what the in a period of time in the machine learning, there's kind of a class of model called like a kernel-based model or generalized linear regression, right? Where instead of having a linear regression on the x, you want to have some like basis of x, and that you're operating on the basis of the x to solve problem, and where you could convert the basis of x into some type of complex distance between points. And so your kind of kernel-based method effectively learn a very complex distance metrics over your data space. So this covariance function here actually has a potential of being extending to unlimited number of dimension of a number of basis function, because it directly measures the pairwise distance, basically pairwise metrics, and you could come up with different functions for this pairwise matrix or kernels, which can be decomposed into unlimited sets of bases. So this gives the kind of power of, this is also what result in a kind of strong power of GP model, because of its kind of using the unlimited sets of basis functions. Several popular way of defining the covariance matrix. The first is using dot product. Or usually you could also define like a more general distance matrix, just call it kernel. So this is one example of using the dot product of the kernel itself. However, there's also other way of defining kernels which directly rely on maybe Euclidean distance of the two or some other metric, as long as you can define a distance. But here is kind of, you can consider like Euclidean distance or just like absolute distance between the two being a very strong metric for distance. So let's just note R as the absolute distance between 2 points. We call like a isotropic covariance function if the kernel or the covariance function is only a function of the distance between the absolute distance between the two. And this is actually a very effective family of kernel functions called radial basis kernel functions, which essentially have this form here. Sometimes you also have like a constant in the front, alpha or k, and it's kind of a function of the square, like the squared arrow between, squared distance between a point. And we can also define stationarity of this Gaussian processes. So if your kernel function or covariance function is a function of x minus x prime, you can also kind of prove that it's like a stationary process. There are a lot of different ways of defining covariance matrix. Perhaps the most popular family is this radial basis family, where the first option is actually effective by itself, and and this Mattern class use kind of another family, like a Mattern family, which they can also prove that in the extreme case, the Mattern class will fall back into a squared exponential or normal RBF. And there's also like neural network kernels, which essentially you can make use of the neural networks to learn a kernel-like function for Gaussian processes. And there are also like periodic kernels if you maybe want to inject such periodicity into your prior. So yeah, you can see that for basically different kinds of covariance distribution can already define like not necessarily the shape, but like like how curvy or how connected, how correlated the function could be, like even without any label point or mean estimate. So these are all like a random draw of these Gaussian processes, assuming mean value of 0 and the covariance function defined in our previous slides. So you can see that different covariance function have kind of this prior inductive bias of how drastically the function fit to the local function of each point, and how much they vary in general, like how big the variance you're expecting like overall. And you can see that this is kind of the more general version of radial basis kernel, where you have essentially two hyperparameter. One is the k. It's kind of like determining how overall, like the variability of the function space. And there's also a sigma, which can call sigma here. It determines like how curved or how local you want the function to be. So basically, the bigger the theta is, you could imagine the function being more smoothed out. Where the smaller the theta is, you're like this distance being kind of amplified by dividing by the theta square, and so you basically stay into more like local to be around, like basically you don't extrapolate too long into the neighbors when you reduce the sigma. It's also kind of like the neighborhood function that we discussed like in the T-SNE lecture, or basically how much in the neighborhood you influence or you're getting influenced by. So given that these are like hyperparameters, you do need to train the Gaussian processes, even though like if you're given this hyperparameters, you entirely define your function. You don't need to train it. But when we say we train a GP function, it's usually mean we train these hyperparameters such that the hyperparameter is bestly fit to our given training data. So assume that we have some training data and we figure out the best hyperparameters that we use to fit the data. The next step is to run the inference. So assuming that this data set is of x and y is given, now that you give a new sets of point x star, we ask the question like, what is the predicted value for x star? So as I said, if we assume that all of the points that observe the training data and the new point x star comprise of Gaussian processes, then they should be they should have this joint multivariate Gaussian probability. So the problem of doing inference on x stars essentially becomes a problem of doing a conditional Gaussian multivariate Gaussian of y star, conditioned on the value of the x being y. So this is what I said, like conditional multivariable Gaussian problem, where instead of just model everything as a joint, you set part of them as fixed because you know the value already. A condition on this value, what is the posterior value of the new function, the new points we're querying here, which is the y star. So you can see that the y star, again, is a Gaussian distribution, and the mean of this Gaussian distribution and the variance both they both depending on the value of the training data, which is the y. On the other hand, they're also depending on the kernel function of how you define like how the things will extrapolate across these points. So you can consider kind of the mu here becomes like the prior mu, and this is the new mu, which is the training data that you observe, and you're subtracting the difference between the training data you observe and the prior model you assume, and you weight this mu by some distance, and the distance is this kind of kernel function that you define over the space. So it's kind of like the weighted mean, or sort of like k-nearest neighbor with some soft weighting. So essentially that's what the mean part is doing, and the covariance, again, is kind of also making use of these joint Gaussian processes assumption of the model. So everything here is closed form, and the cost of this model is mostly on this see the estimation part, because this is a pairwise function, and you need to compute this for all pairwise data between the training data and the testing data. So this part essentially gives you kind of a n-square complexity. And a lot of time, if this kernel function is very involved, it could involve a lot of like multiplications and additions in the compute. So depending on what kind of kernel you're using, it might be able to speed it up with GPU kind of parallel computing or not. All right, so I hope this. I think this is a little bit maybe new to questions.
Sorry, just a question. So the original problem was there are infinite number of functions that I can fit over like 3 points, for instance, right?
Yeah.
But here you can choose infinite number of the kernel. Like, how do you choose the right kernel?
So the kernel, the kernel is a function of the points. So you can choose the kernel by training as I said, like there are 2 parameters you can train or tune in your kernel. And you're basically tuning those kernel on the training data to find the one that best explain what you observed. But you can see that with this model here, you are able to generate unlimited number of functions because it's a distribution word function and it's not a single function. So I mean, there are unlimited way of extrapolating for sure, but the question is how you can define a distribution for that unlimited way of sampling. And the intuition here is we want a distribution or function such that the further away you are from the data, the higher variance you'll be expecting. And that's what this kernel function is kind of defined in terms of generalization. Yeah, I agree that it might not be the best family, best predicted function, but it's kind of the best we can come up with already with a prior that is designed like this. Yeah, without such prior, we have, like I think deep ensemble is, it's kind of like a more relaxed prior, like you just randomly sample function and you optimize, right? But essentially you're still sampling from some distribution there. So it's also like some inherent prior function, even if you're using a deep ensemble model. So here is the same thing, but the prior we're defining is over a Gaussian family with this covariance matrix. All right, cool. So just a summary of what we've talked about so far, like Gaussian processes, or also oftentimes abbreviated as GP. It defines a distribution of functions such that we can, at every single point, we have an estimation of a distribution instead of a single point estimation. And they're actually closely related to a lot of the method in kernel learning or like generalized linear regression with kernel and basis. And it also has some relation with deep neural networks. And there also people try to prove that Bayesian neural networks is one kind of Gaussian processes in a generalized fashion. And now that we have a function, and we know that we can use this function to do posterior inference, how we go about designing the acquisition function for Bayesian optimization, right? So essentially, again, this is kind of the iterative procedures of Gaussian processes. I think what the new content here is what explicitly define exploration and exploitation is, where the exploration is usually kind of like you try to hedge your bet to reduce the uncertainty about the model itself. So it's usually a function of variance, where the higher variance means higher uncertainty. So when you do exploration, you want to kind of rely on higher uncertainty. Versus in exploitation, you want to get to the actually optimizing the problem. So we will lean towards things that has higher mean, because mean is actually like telling us about the value of this point. So a lot of these acquisition function we will see inherently will be like the sum of function of the two term variance and the mean in some sense. So this is another visualization of this process where we can see that with a smaller number of points, we have like a lot of uncertain space. And if we use the function to pick a point and we observe the value of this point, we effectively reduce the uncertainty in this area. And there's a chance that we actually have improved value, but there's also a chance that you have a bad value. But at least we gain some information about the function in that case. So there are certain acquisition functions that mostly can be computed immediately once we have the Gaussian model. So some of them involves, like the first is called probability of improvement. The second is called expected improvement, which we kind of covered a little bit previously. And actually the third one is also, which is also very commonly used one, is called upper confidence bound. We try to balance between the mean and the variance. So just a closer look into probability of improvement. So remember that we have a distribution of values, and at each point we know the exact distribution given the Gaussian form, right? So assuming that we have x plus, which is the current best point, which is this red point here. So if you draw a horizontal line, the probability of improvement is basically how much, or the cumulative probability of that PDF you defined locally at that point, such that the value will be higher than this x plus point that you defined. So like this, so this is effectively using both the mean and the variance of the estimation, but it is kind of still only care about improvement, like the upside on the value. So it could be sometimes a little bit too greedy. So people can also add a little bit of noise here, or epsilon. It's kind of like epsilon greedy, that you allow slightly, if you're not fully optimizing, if you're slightly de-optimizing, but if there's enough upside, you still want to hedge your bet on it. And this epsilon is kind of like the trade-off between exploration and exploitation. And the second previously used question? which function you're talking about?
The second one, with the noisy one.
This one?
Yeah.
Oh, this is an example of optimizing when you maximize the function. Right, so
But even if you optimize, you have, because you add the noise, it makes sure it's slightly optimized. But if you to add the negative one, so it will be ensure to make sure this model not over than the maximum number or something.
oh, this value can be negative.
Oh, okay.
Yeah. So yeah, I think yeah, if you make it positive here, it's kind of making it more stringent. Versus if you make it not negative, it's kind of loosen up the criteria.
On the bottom graph, is that?
Yeah, this is only using positive. Oh, sorry. So I think so. The epsilon here is the probability of this thing plus the epsilon. So it's not directly adding this to how do you explain that? You basically give some value to everywhere. It's not a function of how much you're bigger than the best, but you're giving some function to giving some probability mass to all the places. So essentially, you kind of want to add this part such you rely less on your mean prediction, but you rely more on your variance prediction. Because you add this term to everywhere, then it's the variance that's kind of giving you the relative like margin of where you want to explore or not. So you basically how much you rely on the variance term. Because if basically if you choose something that's like totally irrelevant, then it's 100% at all positions, right? So then it's only the variance that's determining where, like whether or not this term will be amplified or not.
The variance is it depends on the distribution of f(x).
Of what?
f(x).
No, the variance is a function of the x.
It's not the distribution from the f(x), the distribution.
So sigma and mu defines the distribution of x, but it's only depending on it's a variable. Yeah, the variable is x. All right, so the next acquisition function is expected improvement. So instead of calculating the probability, you directly marginalize on this estimated distribution, and you just compare if after marginalization the mean is better than the current best observations. And again, it also have a closed form, assuming you have access to this Gaussian distribution. So this is this is kind of leveraging the variance directly, because the mean is if you're more uncertain about this value, then it's likely to impact the mean estimation of the point. So the upper confidence bound is a more obvious way of like balance between the mean exploration, which is the variance, and the exploitation, which is the mean. So it's effectively just like directly calculating the confidence bound by like adding or subtracting the variance by and weighted by a certain beta, which beta is basically how how much confidence you want to consider. So this is also like a hyperparameter in Bayesian optimization. So again, like even Bayesian optimization itself has some hyperparameters that you kind of need to tune and figure out during the course. And one interesting observation is in the field of bandits, which is a slightly different problem, where you can consider bandits as you have like k different actions that you can roll out each time, and each action is related with some noisy reward function in behind. So each time you could maybe pull one of the arm in the bandits to get a estimation of the reward. And across time, you will also have some notion of uncertainty, where uncertainty there is defined as like how frequently you have visited this arm or not. So in the bandits, they also have this upper confidence bound function, where it's try to basically explore, like let you try to explore this arm if you haven't used this arm for a while, and therefore your value function about this arm can be uncertain. So people try to also do like analysis between, try to find some basic synergy between Bayesian optimization and bandits. So there's a whole realm of theoretical world that try to study these two worlds, and it's actually they share a lot of commonality. And in some sense, if you frame the Bayesian optimization problem, for example, especially when you're searching over a limited space, well, for the Bayesian optimization problem, you can also frame it sometimes as a bandits problem, and they're showing that running this upper confidence bound kind of is minimizing the regret, where the regret is the difference between your current optimum and the true optimum. So there's a little bit kind of more theoretical guarantee added to the UCB in the view from bandits. So this is kind of a illustration of different types of these acquisition functions. So again, so the UCB is the one that effectively leveraged the uncertainty better, because kind of you directly like factor in the uncertainty, and it's more upside towards uncertainty. So a lot of time UCB, I feel like a lot of time I would use UCB out of the other ones because of the the better emphasis on exploration. Besides these ones, I guess the good property about these acquisition functions is they are very cheap to compute, right? So at any single point, you can directly evaluate them just with a one forward pass or one posterior estimations. However, like if you consider like Bayesian optimization as like a long-term optimization problem, you kind of also want to maybe analyze the effect of future rounds. So you kind of want to look even more further ahead and see if you can simulate the effect of acquiring certain points and like how much influence they will have on your acquisition function. So that gives some motivation to more advanced or newer acquisition functions, two of which are called knowledge gradient and entropy-based sampling. So one thing that we have to understand is the X star is not it's not a single value. The best observed point X is a single value, but the best point of your entire function is a probability, because we have a probability over functions, right? So the optimum of that function is also a probability. So effectively, you actually have this distribution over the optimum of your current Gaussian processes, and therefore you can measure the entropy of that point. Basically, where your optimum spread out. Like if your function is super certain, it's very likely that you're already focusing on one area. So your entropy on the optimum of this Gaussian processes is lower. So then this entropy search is basically try to say, like, if I query a new point and add it to my training set, how much entropy I can reduce hypothetically of the prediction of the distribution of the maximum of the Gaussian processes. So this involves one step ahead. Basically, if you at each point you want to query X, you need to first roll out the prediction for X, which is the fx, and you add fx into your training set, assuming that fx is maybe what the label you would get as an actual outcome. And then you reevaluate your GP function, and then you can get a new estimated, basically new estimated entropy of the optimum of the new GP function. So the entropy search try to find the points that will effectively reduce this entropy or uncertainty of where your maximum could be. by using the hypothetical value of this point you query. So the difference between the previous sets of acquisition functions, you need to basically update your GP. You do kind of a pseudo update of your GP, assuming that you have this new point and you have some value of this new point. Similarly, the knowledge gradient is effectively similar, where you want to ask like how much I can improve the best value of my function. So instead of looking at the entropy of the P of x star, we just directly look at the mu of the x star and see if I add a new point using its like pseudo label predicted by the current model and re-estimate the Gaussian processes would be the new optimum B and how much improvement like upside there could be. Thompson sampling is something that's more closely related to bandits, but what it does in bandits is basically you can assume that you have like k different arms and you have some prior function over the arms already, or posterior function over the arms. So what you do each time is you sample one of the you sample one of the functions of the estimated value over these arms, and you execute the arm that maximizes this sampled value function. Similarly, in Bayes optimization, if you have a GP family, for example, each time in the Thompson sampling, you could sample one function from the Gaussian processes, and then you greedily optimize that sampled function. And by drawing different functions of your GP family and doing different optimization, you're getting kind of a batch of different points that try to hatch. You get some uncertainty or exploration out of the effect that you're sampling different families. So I think Thompson sampling is a very interesting approach, especially in the batched BO setting, where also it bridged the BO with bandits, and has a very nice theoretical proof in the paper that's written a few years ago. All right, so a lot of the math on this part, but I think essentially people use effectively what proved to be quite useful is the upper confidence bound function and the knowledge gradients. Effectively that's what I personally experienced that are pretty effective in balancing exploration and exploitation. But if you consider the different acquisition function being your hyperparameter, right, you could also effectively try to search along these different designs if you have some budget. So as some examples, Bayes optimization has been used in both molecule design for small molecules and optimization of large molecules like enzyme and other protein fitness to optimize for protein fitness. This is a very popular example. I think it's come up by Google and some folks in Harvard, where basically to run up Bayes optimization, since it's still like an optimization problem, how we optimize acquisition functions is through like gradient, actually through gradient optimization. So you can see that it's easier if the thing is located in a continuous space to deploy gradient optimization. So, but molecules are usually discrete. So the way they carry out Bayes optimization is they first train a variation autoencoder that converts the SMILE strings, or sometimes you can also maybe do a graph encoding. You can convert the 2D graph of small molecules into a latent space. And then they just train the Gaussian processes over this latent space for the small molecules and deploy this Bayes optimization with UCB. And they show that if you're guiding this optimization with certain property prediction like QED or SAS, they were able to, with some number of acquisitions, they were able to sample like molecules that has much improved quantities for these predicted properties. And there's also Bayes optimization for chemical reaction design, where like in the reaction you have a different space to search like what ligand you use, what like solvent you use, and temperature. Those parameters can all be set as a feature to your Gaussian processes. And effectively they use this Bayes optimization search to come up with the best reaction condition for a certain outcome they want. And in terms of protein fitness, there's also like very classic paper on like try to navigate the protein fitness landscape. I believe this is certain like enzyme family, and just treating the protein sequence as the input like X. They were able to kind of optimize the stability, the thermal stability after 6th round of like upper confidence bound acquisition. All right, so we still have some time. I want to move to talk about reward optimization approach, where so effectively I think our RL itself worth like an entire a new course. So there are very good courses offered by, for example, Professor Jiang Nan Jiang in our department. But I think what I'm going to cover is just kind of very basic of RL in case like some of you might be new to this topic. So the setting of reinforcement learning is slightly different from Bayesian optimization, but the goal was still have a mindset of optimization. Why I say that? Basically, a lot of the RL involves this kind of MDP setting where you can consider instead of having like a single like Gaussian process of X and Y, you have a more involved decision process, which is also iterative. Where basically you're interacting with some environment with an agent, and the agent will be able to conduct some actions, and the agent has basically where you are currently is can be known as a state. So a state is like your current partial solution or the solution that you currently are, and with the agent you will be able to roll out an action that effectively will change your state from current state to some other state. And this transition function will be determined by some underlying world physics that's driven this change. And after you roll out certain actions and move your state to a new state, the environment will respond to this change and give you some reward. And the kind of the overall goal of RL is to come up with the best possible policy, which is a probability over what action you roll out at each time, such that your expected reward you get from this environment is maximized. So in the protein design, so this like Markov decision process, what the Markov means is basically you're assuming that you roll out this sequential of actions, and the transition of the state is only depending on the previous state and the action you roll out. So effectively, by executing multiple actions in a row, you have this kind of Markov process where you can easily compute the likelihood of this process by multiplying together your policy and the state transition matrix, and you can define kind of the joint likelihood of this entire Markov chain by multiplying up these probabilities. Yeah, in the protein engineering or molecule engineering regime, what you can consider policy being or action or policy being some proposal of actions that modify your sequence or extend your sequence, however you can define a sequential process of generating or altering the state of your protein. Considering like a protein language model, especially like GPT type model, you can consider basically the autoregressive generation process of a protein sequence being kind of a sequential policy of generating a certain protein. Or in a mass language model regime, you could also consider the process of masking and unmasking a certain position as like an action. And you can also define some kind of likelihood function of a sequence of action you take. And in terms of the reward, again, like a lot of time you could directly try to fit a function over the reward. That's also happening in the reinforcement learning space as well. But in the most extreme RL case, you can imagine that you only get a single value, a scalar value from the environment. And the environment could be like in situ experimentation or very expensive in silico simulation. And you just effectively use that reward in your RL objective, such that effectively you try to basically if your modification of your sequence is effective, you should be able to collect higher reward in this process. I think language model is kind of one way of doing the generation, but there are also like more involved way of doing actual like modification of molecules. For example, you can consider like a 3D graphs or 2D graphs, right? How to change your current solution to a new one is more involved than just using a language model to roll out probability, right? So there you actually have some non-differentiability in how you would actually optimize this molecule, which have to, therefore you have to use kind of the reinforcement learning regime to carry out this series of optimization instead of using Bayesian optimization kind of approach, which still relying on the gradients or the differentiability in your input space. A single example is like if you want to break a bond or add a bond to to a small molecule, right? That's not effectively to be written as a gradient update to your molecule space. It's easier if you just write it as like a policy that at this point I want to add something to between these two atoms. Questions here?
For something like this, do people still like encode into a latent space?
In this case, you don't need to encode to a latent space. Yeah.
So you just directly
Yeah.
explore on this space.
Exactly, and that could be a benefit of using RO in that case. Yeah. Question?
So for this example, because the Markov property only depends on the previous modification at a certain spot, right?
Yeah.
So can that just be like the correlation or even partial correlation between these two spots? Like,
Partial correlation.
yeah, like just correlation between these two spots, like.
You mean how you want to how you want to parameterize your policy model?
Right. It doesn't depend on the previous all the modification except for the previous step, right?
Yes. Yeah.
Except for the last step.
Yes. So that's kind of true in, for example, autoregressive model. You only rely on your previous partial solution, and then like small molecule editing, you kind of incrementally adding like things to the molecule. So it's also some sort of like Markov. I think in some sense, yeah. So this Markov thing, it can be defined either as between two state in terms of from a partial solution to a complete solution. It can also be determined as over like any time series or like basically a sequential operation. Even for a diffusion model, for example, right? You could also define a Markov chain. Because in a diffusion model, even though you're not building up from a smaller solution to a larger solution, you're kind of denoising from completely noise to completely unnoised example. But each step in the diffusion transition only depending on the previous time step. If you're taking kind of the Markov chain, the earlier diffusion denoising probabilism model, it's basically another Markov chain as well. And that's why we're seeing RL or RLHF being deployed to diffusion a lot in protein design these days as well. Cool. So the RL algorithm is somehow very similar to actually Bayesian optimization framework in the sense that in each cycle you're making some samples, you're fitting a model, either directly fitting some objective that will impact your policy, or you're feeding some value function similar to a surrogate model. We're learning object in Bayesian optimization. And the third step is improve the policy, which is different from Bayesian optimization, where you directly go for solving the optimization problem. And here instead you solve a modification to your policy, which indirectly solve the optimization problem. And a very simple example is like you just directly compute the likelihood of the samples, right, and then compute the overall like reward you get, and just directly backpropagate through that. So there are different ways of doing RL. I'm not going to talk about all of them, but essentially, I think largely there are like fixed point iterative approach that rely on, for example, value iteration or policy iteration. The high-level mindset there is because RL kind of is a non-myopic long-term process. The goal here is to try to extrapolate or predict into the long-term return of the current state by feeding these kind of value function or Q functions, and use these functions to update your policy or directly, come up with a policy that maximizes these local bootstrap of the values. And the other way is to directly optimize the policy, which is a family of models that are more commonly used in our use cases. where we can call, basically it's called direct policy gradients, where you essentially just directly optimize this expected reward with respect to your policy. And of course, there's like actor-critic and more combined methods that try to use the best out of both. But essentially, I think when we decide what RL to use, we have to understand the problem better and see which part is the limiting step. Like, is it a sampling part that's more harder to conduct, or is it the estimation part that is very difficult? So different RL functions have different, algorithms have different properties. And one key kind of separation of different RL setting is this on policy and off policy RL. Basically, like because the function that we're estimating or optimizing is usually a function of the policy or expectation of the policy. Sometime if we have the data that is collected with a different policy, an example could be if you have already some data curated previously, which you're not using your policy to collect them, but somehow they're just there and you want to use them. This is called kind of the off-policy setting, which is very likely to happen, especially in the first round in our case. All right, so there are a lot of different RL algorithms, and I think the one that I want to emphasize here is called policy gradient, or the reinforce function. But essentially, like if you write up the expected reward function, it will be a function of your reward multiplying by the policy, right? And then you have this integral that compute this marginalization or expectation. However, taking a gradient with respect to this integral is not trivial. But there is a very smart trick called the log trick, where effectively you just take a log of, if you take the gradient of this directly, it can be decomposite into the probability times the gradient with respect to the log of the probability. So this is a trick that you can apply here, such that you could basically exchange the expectation inside to this gradient operator. What I mean is, effectively, you change the gradient of an expectation into an expectation of a gradient. So which is easier to estimate because you can just roll out some samples and estimate the expectation and compute the expectation of, and you can compute the gradient for each sample you roll out. This is kind of the fundamental support motivation of policy gradient. Yeah, and then the algorithm itself is just like break down this probability of trajectory into multiplication of your policies and the state transition function. Remember, like in protein case, the state transition function is 100% fixed a lot of the time, because like if you want add a bound, then you just add a bound. If you decide to, like roll out A for the next character, you directly add it to your state. So there isn't really this stochasticity here. So. But even if there is, you could usually this is not a function of the theta, so you don't care about it. So at the end, it's just a multiplication of your policy and the reward. So this kind of reinforced algorithm is basically like sample some data and then compute this expectation of the reward multiplying by this multiplication of the different steps of your policy, which in the log space is the summation, and just directly do a gradient update. And there are a lot of extension to this algorithm by how we kind of bound the difference that you could go within each single step, because each single step you kind of go a little bit off policy from what you're estimating. So a lot of this later variance, like trust region optimization or PPO, they try to kind of bound how much you can vary in one step. Yeah, and then I think an interesting observation is the connection between policy gradient and maximum likelihood. So yeah, first of all, policy gradient is the only RL algorithm that directly optimizes the expected reward. Like essentially a lot of the other variant, like value iteration, other iteration, they kind of using some dynamic programming solution that approximately solve the problem, but they're not guaranteed to solve it a lot of time. But policy gradient is directly optimizing the expected reward, so which gives it some kind of benefits.